about supervised learning, and that too training a multi-layered feed-forward network. Training single-layer network is quite easier because both input and output nodes are visible to us. Since nothing is hidden from our from user point of view, that's the reason framing learning algorithm is quite easy for networks which are having which doesn't have any hidden layers. So when we move on to multi-layered network, obviously there will be hidden layers which are hidden from developer point of view or user point of view. So you need to train the nodes which are not visible to the user. So the more the number of layers, the complexity of the algorithm will also increase. So we have discussed about supervised learning algorithm, and the importance of setting different parameter values before applying a backpropagation algorithm to train a feed forward multi-layered network. So in that we have seen so how when you present an input based on random initialization of the weights and proper choice of activation functions, how actual output is generated, and then how it is compared with the desired output based upon which some error is generated, and how the error is propagated backwards, and weight or strength of connections of each and every node, how they are modified using the weight modification rule that has been derived. So it's a very, since for each and every pattern, if that multi-layered network consists of 100 nodes, then obviously you need to modify the weights of all these 100 nodes for each and every sample presentation. So imagine the complexity if the training set consists of 1,000 samples. It's not just presenting one sample at one time and then you complete the training process. Generally, it has to go through several rounds of presentation to complete to achieve the desired result. So, I mean, it takes good amount of time to get a solution using though it is more accurate, and for that reason, to train a network which is used for supervised learning application, still majority of the researchers prefer going for the backpropagation algorithm for all the merits it has. But the only problem with this one is it takes good amount of training time to converge it to a solution. If your initial choice of weights are not selected properly, then huge time is consumed in getting the desired result. There are several other multi-layer networks which have been proposed, which can do similar purpose as backpropagation algorithm does in reasonably good amount of time, but accuracy is to be sacrificed. So though not that accurate, though it doesn't produce as accurate results as a backpropagation algorithm gives, these networks or algorithms are also capable of giving good results in a reasonably good amount of time, provided if some accuracy is tolerated. So applications where you don't need that accurate results, you may need not apply backpropagation algorithm all the time. You can choose these alternative learning mechanisms also. So we'll be discussing two such mechanisms here. One is multiple adaptive linear elements. Other one is radial basis functions. Multiple adaptive linear elements, we call it as Madeleines, and multiple Adelines. Already you know what is adaptive linear element. Adaptive linear element is a single node which is used to perform the classification task. But the difference of this adaptive linear element when compared to perceptron is, in perceptron, as soon as you apply the activation function, you just check whether it is correctly classified or not. If it is not correctly classified, then you modify the weights. That means weight modification is based upon reducing the number of misclassifications there. Whereas in adaptive linear element, training happens in two phases. In first phase, we try to, we don't see whether the sample is correctly classified or wrongly classified. We give the input. Suppose you have 100 samples, you give each 100 samples one by one. You generate error. Even though if it is correctly classified also, we modify the weights and see that total error for all that 100 samples is minimized to certain value. Once it is minimized to the threshold what we have fixed, then you go to the second phase and solve the classification problem. So if error is reduced, if error is 0, then it's a perfect classification. If error is not 0, reduced to reasonable good amount of time, approximate estimate of samples will be correctly classified. So adaptive linear element is a solution to apply for linearly non-separable problems. Anyway, perceptron can't solve. Using adaptive linear element, you can get a reasonably good solution for a linearly non-separable problem, though it doesn't give you a solution. So here also multiple adaptive linear elements means instead of single node, in backpropagation algorithm, it's like we are considering multiple perceptrons, multi-layered network. The performance of each node, it is similar to a continuous perceptron if you use a continuous activation function. Here, similarly, in multiple adaptive linear elements, you have more than one. I mean, it's a 3-layered network if you count the first layer, which has hidden layers also. But each node represents a single it operates on the principle of single adaptive linear element. So multiple adaptive linear element is a combination of many Adelines. Learning algorithms for Madeleines have gone through 3 stages of development. We'll be studying about M1, M2 and M3, multiple adaptive linear element 1, Madeleine 2 and Madeleine 3. So as an initially very basic algorithm has been proposed, which is used only for certain applications. Later on it is improvised, and later on understanding the problems, it is improvised further. It has gone through 3 stages of development. All 3 algorithms adhere to the minimum disturbance principle. This is basically on which Madeleine will operate. Minimum disturbance principle. So it has been proposed by Widrow. What exactly this minimum disturbance principle represents is, instead of, see, we have seen backpropagation algorithm. We, based upon the error, we modify each and every weight of present in that particular network. Whereas using this minimum disturbance principle, we don't modify each and every weight. So already when you give the input, you are computing some net weighted sum of the inputs. We try to find out the, based upon random choice of weights, we try to find out the node which has less net weighted sum of the inputs. And we try to modify we reverse the output of that particular node and see whether it improves the result or not. If it is improving the result means whether error is reduced or not. If error is reduced because if we take a discrete application where outputs are just +1 and -1, so when you give an input, for that input, desired output would be either +1 or -1. So you should get +1, but you are getting -1. We try to modify the output of one node and see whether changing the output of node is making the output of the entire network from -1 to +1, which is nothing but the desired result. So then once error is reduced, then we go back and modify the weights of only that particular node, not all the nodes present in the network, to get the desired solution. So minimum disturbance means we are disturbing only the desired nodes to get the required result. So in backpropagation, whether it is required or not, we modify all the weights. Here only the nodes which can improve the performance of the network are modified. That's the reason we call it as a minimum disturbance principle. Then the question is, how do we select the nodes? How do we know, like by modifying weights of these nodes, performance is improved? So for that, since we don't have any specific mechanism for that, we examine the possible result of changing the output. If the change results, suppose we randomly select one node, if the changing the output of that node is going to reduce the error, we try to modify the weights coming to that node and see that change is going to happen. If it is increasing the network error, we discard and try to move to other nodes. So in selecting that nodes, we select the nodes which has got least net weighted sum of the inputs, because changing output of that node is easy. Suppose output of a node is something like 1.8, output of other node is 10.2. You want a negative value to come at the output of that node. It's easier to modify 1.8 to -0.2 rather than modifying 10.2 to -0.2. That's the reason we select the nodes which has lesser outputs, magnitude of outputs, than the nodes which has greater magnitude. The reason is we can do the modification with reasonably good amount of time. Okay, this is the architecture of multiple adaptive linear element one, where rule one is applicable. these are x1, x2 are inputs which are given to the input nodes, and a hidden layer, it consists of a set of adaptive linear elements. Here we are just showing two. You can have n number of adaptive linear elements, and output node is a fixed logic gate. Here it is, in this example it is shown as OR gate. It can be any gate depending upon the application, or you can also have a majority gate. So majority, whatever be the majority of outputs of these adaptive linear elements, that is the output of this particular node. So output layer nodes are fixed. You can't do anything here. You can't, because based upon the inputs you get, output is decided. No training is happening at this node. So you have fixed output layer nodes, which is limiting the performance of the multiple adaptive linear element network. Suppose if you have an OR gate, here we are just showing two nodes in the hidden layer. Suppose if if you are giving inputs as 0, 0, for the random choice of weights, you are getting output as you should get output as 0, but you are getting output as 1. So so to change the output from 1 to 0, you need to modify outputs of all the nodes wherever you are getting 1. Then only your output will be 0. Suppose if your input is 0, 1, 0, 1, your output is 0. Actually, it should be 1. In that case, to get this output of 1, it is enough if you change the output of one node from 0 to 1. That is enough, because you'll get the output of both adaptive linear elements are 0. That's the reason you are getting output as 0 for the input 0, 1. So changing output of this node is enough to get the desired result. You don't need to do you don't need to modify the outputs of both the nodes. That is what the concept of minimum disturbance principle. We modify only